Mhm. قل لي كي تحط l'enregistrement, je démarre. Hein.
C'est bon, David.
Ok, on démarre. Hein. Okay, today we welcome Mohamed Ali Hamza for this new webinar. Mohamed Ali Hamza is an associate professor in the Imam Abdurrahman ibn Faisal University since 2015 and a full professor at the Tunisian Malar University since 2022. He was also associate professor in Saudi Arabia for 2016 to 2022. Mohamed Ali Hamza teach at Nanterre University and the Paris University in France from 1999 to 2002, and he obtained the PhD in mathematics from the University Paris 11 in France. The research topics of Mohamed Ali are blow-up for semilinear wave equations, third-grade fluids equations, existence and stability of solutions for some semilinear evolution equations, propagating fronts, self-semilinear solutions, and he published almost 30 research papers. Thank you, Mohamed Ali, for accepting our invitation, and you have 50 minutes to present your work. Thank you again.
Thank you, Nabil. Thank you, Nabil, for your nice presentation. Thank you also for your kind invitation. Today, I will talk about the blow-up rate for some nonlinear evolution equation without scale invariance. It's a joint work with my colleague Hatem Zak from Sorbonne University, Paris. I will start by introduce the problem in general, then I'll try to define the meaning of blow-up and the meaning of blow-up in particular for some elementary cases like the ordinary differential equation. After that, I will talk about the scaling case. That means the case known when a equals 0, a is a parameter will appear later. After that, I will talk about the main results and I'll give an idea about the proof. Finally, I will do some discussion and I will talk about future works. In fact, for physical problem, it is very interesting to know if we have a global solution or if the time is finite. That means we have a blow-up solution. We have this. It depends of the initial data, and it depends also about the parameters involved in the equation. Once we have a nonlinear ordinary equation, of course, this problem provides, once we have nonlinear, at least we have a nonlinear ordinary equation, or even for some evolution like the equation, the wave equation, Schrödinger equation, also for more evolution systems. The easiest case for provides blow-up is this linearity. Here we have absolute value of u to the p minus 1 times u. P is more than 1. This is called the pure case, which is the easiest one. Why it's the easiest one? Because we have a scaling. That means it's an homogeneous expression. This function is homogeneous. However, if we have something a little bit more general, once the function, the behavior of the function is like that, but the function can be not homogeneous. We can think about, for example, u to the 3 times u plus u squared, which is like that near infinity. Then we lose how the scaling in this case. then the problem becomes a little bit, as we will see later, becomes a little bit more complicated once we lose the scaling, but we have at least the scaling of the leading terms. That means it's equivalent to the u to the p minus 1 times u. The general case is the following. I will talk about it today, is once the nonlinearity lose also the scaling of the leading terms, as we will see later. For example, if we take u to the p ln u, here we lose also the scaling, then we don't have, we have no scaling and no scaling of the leading terms. However, we have the asymptotic scaling, namely, we have somehow u to the p times a slope function, L of u. You can think about ln u, or even an iterative logarithm, that means ln of ln or ln of ln of ln. Kind of functions satisfy the following limit. That means we have a slow growing of the function, a limit where lambda goes to infinity of L of lambda u divided by L of lambda is equal. For example, this function satisfy obviously this limit. Then we have a kind of u to the p times ln u. Then what happened? What is the situation if we have this kind of the nonlinear? This is our target for today. But before that, I will start by introduce the meaning of blow up. Blow up in general means once we have the size of the function somehow goes to infinity once t goes to some to capital T minus. That means after some times, of course, we have.
Can I? In the
Yes.
last slide, when you talk about scaling, what do you mean exactly?
Here I will talk because in order to study the problem here in order to study the problem, I'll move to a new variable which I will talk about later, Nabil. But here
Okay,
somehow kind of homogeneity here. F of u is equal u to the p times u. Here the function is homogeneous. That means f of lambda u equals lambda to the p f of u somehow. That means here we can skip this limit. F L of lambda u divide here, and here a kind of homogeneity here for.
Okay, I see. Okay, thank you.
But here, as I said, here we lose the scaling, but at least for the leading terms, we have the scaling because the leading terms is somehow this one. However, for this one, as I said here, we lose the scaling and even the scaling of the leading terms because somehow the leading terms becomes non-homogeneous. That's why we lose even the scaling of the leading terms. We will see the meaning of scaling later once we do the transformation. I will talk about it. Then here, blow up means the size of the solution becomes somehow large enough once the solution approaches T minus, where T is the finite type. I start by some easy cases related to the ordinary differential equation. The first one, of course, is the easiest one. If we have u prime is equal u to the p, assume that the initial data is positive, then, of course, we can evaluate the solution. The solution is given by this expression. It's u to the t is equal some constant depending on t on p times capital T minus t to the power minus 1 over p minus 1. Then here in this case, it's easy and sorry. This is the easiest case because we can evaluate, we can obtain the expression of the solution. However, if we take the highest order, that means u second equal u to the p. Of course, once we talk about blow up, we talk about the source term is like u to the p, where p is more than 1. At least we need P should be more than 1. Then u secant equal u to the p. Here the situation is a little bit more complicated, but we can prove easily the behavior of the solution blows up once t goes to capital T, blows up following this expression here, a constant depending of p times capital T minus t to the power minus 2 divided by p minus 1. To fix idea, you can assume p equals 2 in order to simplify. Okay. But right now, somehow the expression is homogeneous, as you can see. The expression is homogeneous because the nonlinearity is u to the p for the first equation from the first example, and even for the second one. The third one is u secant is equal u prime to the p, which is an interesting case. Why? Because here we can prove the solution, the size of the solution is bounded. Why? Because here, remember, at least if p is between 1 and 2, here the solution is bounded. However, the derivative of solution blows up. That means the blows up is related to u prime and not related to the solution, at least once p is between 1 and 2. Then, as you can see in general, T max, which is capital T times of blow up, depends of the size of the initial data. It's inversely proportional. And that means if T max is small, the size of initial data is large. But right now we have u secant, we have an easy dynamic. That means we have the derivative or the second derivative is equal a source term where the sign is clear, it's positive. Then we don't have any competition. However, for the third case, for the next one, here we have somehow the complicated equation, ordinary differential equation. To fix idea, we can assume A equals B equals 1. Even P is equal 3 and Q equal 2, but it works for the general case. Then here somehow we have a damping term, U prime, U secant plus U prime. We have a damping term. We have two source terms. It depends on the sign of B. We have a competition between U to the P and U to the Q. And we have, of course, some initial data. U of 0 is equal alpha and U prime of 0 is equal B. Of course, we have a local solution, and we have two situations. T max can be finite or infinite. It depends. At least we are sure. Of course, we can, if we assume initial data small enough, we are sure we have a global solution. However, if the initial data is large, at least the first component of the initial data is large. By the way, in this case, we can prove this. The solution satisfies this inequality. That means the second derivative is somehow more than half u to the p if we take alpha large enough. And we have a blow up for sure. And the behavior of the solution is stable. That means it's the behavior of the solution is like the case where A equals B is equal 0. Then if the behavior is stable. I'm sorry. In fact, I try to explain why the behavior is stable, at least formally. Formally, if we assume the solution near the blow-up time, of course, the blow-up time depends on the initial data. But if we assume the solution u of t behave like constant capital T minus t to the requested power, which is minus 2 divided by p minus 1, then in this case, the second derivative, of course, once we evaluate the second derivative and due to the p, the behavior, at least formally, I talk right now formally. I will talk about the proof in the next slide maybe. Then formally, u prime divided, if we evaluate, it's easy to, we take the derivative for u prime, u second, and u to the p. Then clearly, u prime over u second is, in terms of behavior is like constant times capital T minus T, which is small enough. Remember, T goes to capital T. Then near capital T, u prime is small related. The ratio between u prime and u second is small. Also, remember Q is less than P. That's why the ratio between u to the Q and u to the P is small. Then formally, the green terms are small near blow-up time. The green terms are small related u second and u to the p. Somehow the leading terms, the terms leading the dynamic near blow-up times are u second and u to the p. I try to give an idea about the proof and where we will see why the scaling is very important. I try to give an idea. Of course, this the proof of course, to prove the solution behaves like constant times t minus t to the power is easy to prove in the ordinary differential equation. But I'll try to do a proof which the generalization will be easy in the case of a partial differential equation, namely once we have the wave equation or even the heat equation. Then the idea is to evaluate the, yes?
Could you please return to the previous page? Is the right-hand side, is it u to the power p or ut, u prime?
Sorry, here the right. No, I talked about u to the power p. Here it's u to the power p.
So the competition is between two power nonlinearities.
Somehow, and we have a damping term.
Yes, linear damping.
No, but once the initial data is large enough, u to the p is large enough related. The ratio, as you can see, is, as I said, you are right, because here somehow we have a competition between these source terms. However, if we start by alpha large enough, then somehow in this case, u second is more than half u to the p. That means you can remove, you can neglect these terms p
the two terms, okay,
which is somehow small related. For once we take a good start, that means we start by initial data with large size.
So it's like mix between focusing and defocusing nonlinearity.
Somehow, yes.
You take B positive.
Here, it's the sign of B is not, it doesn't matter, because I'll focus about the behavior. Once, what if we have blow up here, the leading terms will be u second and u to the p. If
yes.
Clear, if we have blow up, if p is somehow equals -1, then the leading terms will be u to the p. Yeah. Then this is the dynamic of the near blow-up times is given as you can see here by u second and u to the p. Why? Because the ratio between u prime and u second and u to the q and u to p is small. Because remember, t goes to capital T, then this term is small.
And you take p larger than q all the time.
Of course, of course, of course.
Okay, thank you.
That means somehow the leading terms is we can put these terms in the right hand side. You can see it, but the sign of V is not important. If we have blow up at time t, then this term is more important than this one. And of course, the damping term is not important. As you can see, the second derivative is more important than the first. I tried to give a sample proof, but as I say, in the case of the ordinary differential equation, we can do better. However, this proof is easy to generalize in the case of partial differential equation. Then here, the idea, and now we will see the importance of the scaling. here we try to introduce W, which is the ratio somehow between U and the expected the behavior. The expected behavior is, remember, like capital T minus T to the power minus 2 divided by P minus 1. Then I try to evaluate the ratio. And I'll use a slow time somehow, which is S equal minus log capital T minus T. Then remember, I'll focus about the case where T is close to capital T. That means S goes to infinity. T minus T goes to 0 plus. Minus logarithm of 0 plus goes to infinity. Then S goes to infinity once T goes to T minus. And somehow this is the slow time. It's called the slow time. I try to rewrite the equation in terms of W. If the expected result, if I have the expected result, that means W is bounded. Why? Because as I said, W is U divided by the expected solution, the expected behavior of the solution, which is this with the power minus 2 over P minus 1. Then this is the equation related to U secant equal U to the P. This is the equation for the pure case somehow. But of course, if we A and B are not equal 0, as we can see here, we have W dot times exponential minus S. That's why here, as you can see, in terms of W, here the fact we have pure power here. As you can see, we have W, we have homogeneous terms here, W times 1 somehow. But here for the small terms, near blow-up time, it's multiplied by exponential minus S. Remember, S goes to infinity, which means these terms are somehow some small perturbation. Even this one, compared to W to the power P minus 1 times W, it's small because it's multiplied by exponential something positive times S. Remember, Q is less than P. Then, as you can see, this is the green terms are perturbation, and the leading terms are given by the particular case where A equals B equals 0. Of course, the proof is based to the construction of the Lyapunov functional. Lyapunov functional, that means a functional related to the equation, and a decreasing function. It's just a decreasing function related to the equation. For the imperturbed case, that means if A equals B equals 0, we define E0 like half. It's the energy. That means we multiply somehow the equation by W dot, and we integrate. Then this is the energy. But of course, we can take care about the perturbation. That means the terms related to the damping term and the other source terms. Then here, unfortunately, the derivative is not decreasing once we have the green term, and the green term is somehow easy to, the control of the green term is easy. However, the red term is more complicated because, as you can see here, even we multiply this expression by exponential minus lambda S, but it's not easy to control it. Then the idea is to add another energy term with the law, which is multiplied by exponential minus R times S. Then somehow here we multiply the equation by W, we integrate, but we multiply by this a small expression exponential minus R times S. R is some positive constant given by the minimum of half, and P minus Q divided by P minus 1. Then it's a kind of correction of the energy related to this perturbation. We have a long computation, but we can easily control the lower terms regarding the energy terms. Once I talk about the energy terms, I mean W dot squared and the W to the P plus 1. This is the energy term, because this one is somehow controlled by this one. The quadratic expression is controlled by the source term. As I said, by this new energy, which take care about the perturbation, is somehow Lyapunov functional. Why? Because we can control this term easily, because by multiplying by a common factor, we can easily handle this term and we can remove it easily. Then somehow we construct a Lyapunov functional, which means we have the requested, that means the energy is decreasing, and even we have control about this term, because we have better than decreasing, we have control about W dot squared. In fact, we will prove once the energy is decreasing, we have two ways. The energy goes to some constant, positive or negative, or the energy goes to minus infinity. We will see it's impossible to have the second case. That means the energy, if the energy is less than a negative constant given by C1 and C2, C1 and C2 are two positive constant, then y of w, which is y squared, satisfy this inequality, which means by using the equation, by multiplying the equation by w, the second derivative of y satisfies the following inequality, which means y shall goes to infinity, where s goes to infinity. However, by using the equation once again, we can prove y to some negative power is concave, which is impossible. It's impossible to have a concave equation going to infinity, as I said before. Here y goes to infinity, which means y to the minus gamma goes to 0, and y to the minus gamma is concave, which is impossible. Then, for sure, my energy is bounded, and of course, I have control of W dot squared. This is a complicated proof related to, we can do better, as I said before, for the ordinary differential equation. But the positive point for this strategy, it works. It's inspired about the case of the partial differential equation. It's a simplified proof of the partial differential equation. Then once we have control about the energy and we have control about the L1 norm of W dot squared, we prove easily W is bounded, and also we prove better it's convergent, namely the behavior we have, W is bounded, as I said before, means the behavior of the solution like the expected, that means T minus T to the capital T minus T to the power minus T to the divided by P minus 1. Then this is to conclude what I said here. I tried to summarize what I said. If we have more complicated nonlinearity, that means if we have f of u is equivalent to u to the p minus 1, even we lose this, the scaling, but the asymptotic scaling is enough that means if we have just the asymptotic scaling, like up times ln u or up times ln ln u, or even just if we have blow up, like 1 over f, in order to have blow up, we need the nonlinear, the source term, the inverse of the source term is L1, then no asymptotic scaling. Then the question is the following: if the asymptotic scaling is important to derive the blow-up rate. The impression is yes. That means it's necessary to have this condition. That means at least we have the leading terms shall behave like u to the p somehow. But we will see it's not requested. That means even for this kind of nonlinearity where we lose the asymptotic scaling, even though we have the answer is no, that means we can handle this. Of course, the idea is a little bit different. The idea is based to reduce the power, the pure power case up to an epsilon. That means somehow here the nonlinearity is more than u to some power q, p plus epsilon and p minus epsilon, and we can construct a sub-solution and super solution. Thanks to this, we got a rough estimate, which then we have a logarithmic correction, namely the behavior of the solution for this kind of nonlinearity is given by this expression. Then somehow we have the same behavior, but we have this logarithmic correction related to this logarithmic nonlinearity here. Then the nonlinearity implies a correction in terms of behavior. This is related to the ordinary differential equation. Of course, this is the easy case, but the main important case is about some evolution equation. Namely, in my presentation, I will talk about the heat equation and the wave equation. For the equation, it's given by dt of u is equal Laplacian u. Then the solution here is depends of x and t plus f of u. F of u is the nonlinear inequality requested. That means we have some homogeneous terms multiplied by log to the power a. A is any real number. It can take positive or negative values. To the power 2 plus u squared. Here we choose 2 plus u squared in order to avoid the problem related to the singularity of logarithm near 0. Then here 2 plus u squared is more than 2. Then this term somehow is more than some constant anyway. For the heat equation, I'll focus about the powers until the Sobolev power. But for the wave equation, we have a gap. We can talk just about P less than PC, which is called the conformal exponent, which is, by the way, less than the Sobolev power. And here for the wave equation, we have a gap. The case between super conformal and subcritical is not clear right now. Even for the particular case, for the pure case, that means if A equals 0. Then, of course, if A equals 0, the problem is homogeneous, and it was studied. I will talk about later. Then why this linearity, this logarithmic correction is important? I try at least to motivate by 2 ways. The first one is a mathematical one. It was introduced by Tau in 2007, where in order to then here somehow we have the power 5, which is the sub in 3 dimension, which is the critical Sobolev power. Then once we multiply by logarithmic, somehow the power is supercritical, even it's logarithmic supercritical. And in order to investigate the behavior or the dynamic in the supercritical case, this is the first investigation. It was done by Tau in 2007 in order to study the global problem and the scattering result for the 3-dimensional nonlinear wave equation. It was generalized later in for any constant c between 0 and 4/3. These results are about the radial case, and later Roy in 2009 proved the iterative case. That means here it's still a supercritical range with log-log, but here without radial assumption. This is the first motivation. Then the first motivation somehow is to investigate a new region, a new bound in a supercritical region, a new region, by multiplying just by the logarithmic term, which is for sure more easy to handle. The second one is the physical motivation. In fact, this logarithmic correction somehow has a lot of application in many branches of physics, as quantum mechanics and geophysics and nuclear physics. We have a lot of application where maybe the nonlinearity is not pure. We have a correction logarithm. In general, we have this kind of nonlinear. Then the question, as I said before, is the scaling invariance property is crucial in deriving the rate. The answer, the impression is yes, but of course we will see the answer is no. That means no need to have the leading term homogeneous. We can even have this kind of nonlinearity, and we can evaluate the blow-up rate easily. Then our goal or our goal is to obtain the blow-up rate for solution for two cases, for the wave equation and for the heat equation. Then for the wave equation, we have some particularity, like the speed of the propagation is finite. That's why it's we should study it in the energy space. That means where where we have control about u, the derivative of the gradient u, and the derivative, the partial derivative of u related to t, in the backward light cone with vertex a, t of a. For the heat, no need, because the speed of propagation is somehow infinity, and we have some regularity. That it's enough. We can study the problem in this L infinity space. I'll start by the wave problem. For the wave problem, as I said, we have the main property, the known property is about the finite speed of propagation. That means if we consider a solution in initial data in H1 times L2 log, we have the domain of definition where the solution is defined is 1 Lipschitz. Why? Because somehow the domain of definition is union of backward light cone. That means if we take any point in the domain of definition, we can draw easily a triangle like that. It's for sure the slight backward, the light backward cone is for sure included in the domain of definition. Of course, in the boundary here, even in the boundary, that means the limit where the solution blows up, it's a kind of graph like that. But we can easily draw the light cone. Of course, in the easiest case, that means if we can draw, we can do better. That means even if we take here, the slope is 1 for this blue triangle, which is the light cone, since the speed is 1 for this equation. But if we can do better, that means even if the slope is less than 1, the triangle is still in the domain. Then here this point is a little bit less singular. That means it's called non-characteristic points. If it's impossible to draw the green triangle, in this case, the problem is a little bit more singular, and we have a characteristic point. In my presentation, I'll focus about the first case. That means somehow the easiest case, where the solution is singular, of course, but it's a little bit less singular than the second one. Why? Because we use we use this the fact the solution is defined in the green triangle in order to improve the result. For the heat equation, the solution is a little bit more different because we have the two main properties. The first one is about the speed of propagation, which is infinity, and about the regularizing effect. That means even if we start by any initial data, if the initial data is L infinity, for example, the solution becomes regular for any positive times. Then here the domain is just given by t between 0 and capital T. And the size, the meaning of blow up means the norm L infinity goes to capital to infinity when t goes to t minus. This is the known result, which is given by Giga and Kohn. And later, in order to improve the powers, because the first result was for some powers, but the full understanding of the problem until for subcritical power is given in the is given later. And we proved the behavior of the solution for this heat equation is somehow given by the ordinary differential equation related. That means by removing the Laplacian u, then until p less than ps. This kind of blow-up is called first blow-up of type 1. It's related to the following ingredient. The main one is, the first one is to use the similarity variable and the equation satisfied by W. Then we multiply the equation by WS and prove the Lyapunov functional is decreasing. And of course, if it's decreasing, it's less than some constant. We have another criterion which implies the positivity of the energy, which implies, of course, the energy is bounded. Then by using some interpolation result and the localized energy, we prove the W is bounded. Remember, W somehow is the ratio between U and the behavior of the ordinary differential equation. Then, as you can see, the result is simple until the subcritical Sobolev power. The solution, the L infinity, the L infinity, U in L infinity times capital T minus T, that means divided by the associated ordinary differential equation, is bounded, which means the behavior of this equation is given by the associated ordinary differential equation. U prime equals 2 to the p. Remember, the explicit solution of this ordinary differential is known. I started by this easy example. Of course, the proof is based, as I said, this is an idea of the proof. Then the first step is to introduce W and this a new variable. The first W is somehow the ratio between U and the expected behavior of the associated ordinary differential equation. S is the slow times, which is defined before. And Y, it's a kind of zoom near any point. Here then x minus x0 divided by root capital T minus T. This scale is related to the heat equation. Then we have a kind of zoom near x0 and capital T. This is the new variable y and s, which is the slope. In terms of W, of course, as I said here, we have the scaling. That's why, as you can see, we have homogeneous expression here. Here we have an homogeneous expression. Ws is equal 1 over rho times divergence of rho grad W minus constant times W. plus W to the power P minus 1 times W here. We have an homogeneous expression even after this scaling. Here the expression is simple. That's why it's easy to multiply by multiplying this equation by WS. We got the following estimate. That means the energy, the natural energy, is decreasing, and of course we can prove it's positive. Then we have control about all terms related to the energy. That means WS, grad W, and even WP plus 1, at least the average between S and S plus 1. Thanks to this, by using basic tools, we can prove W is bounded and even grad W is bounded, which implies we have a blow up with the type 1. That means the solution of the partial differential equation is like the solution of the associated ordinary differential equation. Somehow we have the same, even the situation is different, but until the subconformal exponent, we can construct a Lyapunov functional. That means by doing somehow the same thing, namely we write the equation in W in the new variable Y and S. S is, as I said, the slow time. Y is the scaling, is a kind of zoom related to the problem. And W, it's a kind of ratio between U and the expected result, namely the solution, the behavior of the solution is given by the associated ordinary differential equation. Of course, we show that P is bounded, which implies we have another identity given by multiplying the equation in W by W. Thanks to this, we can prove W in itself is bounded. Then this is the statement of the result given by Merle and Zach in 2005. Where where they show it, the blow-up rate is given by the solution of the associated ordinary differential equation. That means the solution, the behavior of the solution near blow-up time, the behavior of the solution is like the behavior of this, the blow-up solution of U secant is equal U to the P. How much time I have, maybe? Nabil?
Oui.
How much time I have?
It's almost finished. You can, if
Okay,
5 minutes it's okay, we can continue for 5 minutes.
Enough. It's enough. Then, as I
Okay,
said here, we write the equation. Thank you. It's enough. We write the equation in terms of W, and of course we have a kind of energy. We have a kind of Lyapunov energy related to my problem here. That means once the nonlinearity with the logarithmic correction. Here we can obtain the behavior of the ordinary differential equation. As I said, it's a logarithmic correction. And we prove the same result. That means the behavior of the solution is given by the associated ordinary differential equation. That result is published in Nonlinear Analysis in 2021. We do the same thing related to the heat equation, namely, even if the nonlinearity is U to the P times logarithm with the logarithmic correction, then the behavior of the solution near blow-up times is given by the associated ordinary differential equation. Of course, once we lose the scaling, we have perturbative terms were multiplied by some exponential, because here, as we said before, the leading terms are given by the particular case where the leading terms are given by the particular case then here somehow we have some perturbations, the green terms. The yellow terms are a little bit more complicated. The hard terms is the red one, but of course, by using some property and some approximation about the logarithmic expression, we can construct a Lyapunov functional. The main idea is related to the construction of the Lyapunov functional. We construct it in 2 times, and thanks to this, we can control all terms related to the energy. This is true for the wave equation, and somehow we prove the same thing for the heat equation. Of course, the case of the heat equation is a little bit more complicated because in order to conclude until the critical case, we need more estimate. But it still works even for the scale. Then here, the same idea. That means we define, we introduce W, which is kind of ratio between U and the expected. Then we do the zoom requested related. This is, of course, the zoom for the heat equation, and this is the slope. Maybe we can stop here, I think. Thank you.
Just 1 minute. Okay, do you hear me?
Yes,
Yes,
maybe.
yes.
Okay. Is there some questions? Makram, yes, of course, Makram. Go on.
Thank you, Nabil. Thank you, Mohamed, for the nice presentation. It's already many information, good information in the talk. Thank you so much. Just in the, did you present, or maybe I missed the part, but did you present something for the critical exponent, critical value?
You talk about the pure case or the?
Yes, the pure case without logarithm, just the pure case.
For the pure case, it depends. For the wave equation here, as you can see, until the conformal case, it's understood. It's a little bit more complicated, the understanding of the critical case here. But remember, PC, this is the conformal case. Then we have a gap until the Sobolev power. Here, PC, remember, is 1 plus 4 over n minus 1.
Okay,
But
so
yeah,
my question is yeah, for the critical in the sense of Sobolev, of course.
No, of course no. Here for the wave equation, as I said, we have a gap. The problem, we understand the problem is understood just until PC, which is the conformal case. We have a gap for the super conformal case we are working in. We have an improvement. We have some rough result, and we have the weak estimates. But the sharp result is not known until now. That means this kind of information you see, the behavior is given by the associated ordinary differential is not known until the Sobolev point.
So there is
yes,
no partial result even with the radial symmetry or something like that.
No. We have some weak estimate. That means W somehow is controlled by some constant times exponential lambda s. That means here it's some weak results. We work in, but we have some partial result, not yet. It's even for the pure case, the problem is not clear and is not understood. We have some expectation, some numerical expectation. That means this result shall be true even until the Sobolev power. For the critical power, for sure we have a blow up of type 2. Type 2, that means type 1, that means the partial we can neglect easily, we can remove Laplace U for free somehow. But type 2, that means it's the situation is more complicated, and we have blows with the blow up is different than the associated differential equation.
Okay.
Then for the critical power, to summarize, for the critical power, no way to have this kind of result.
Okay, okay.
For
It will be
critical
weaker result. Yeah.
Yes. So we have some construction. We prove in some particular cases we have a blow up of type 2 in the Sobolev critical power. For the heat and even for the wave equation. An important question: what about the critical power in my last slide?
With the logarithm case.
Unfortunately, here, is it possible to expand our result in the critical power when P is equal to PS? We have somehow, if A is negative, we are still subcritical, then, but it's not clear. The problem is not known until yet. Then a natural question, is it possible to extend this result for the critical power when A is negative? When A is positive, no way, because we are super critical, but at least when A is negative, we are somehow still subcritical, then we have, we can expect this kind of result, at least if A is large enough.
Okay, okay. Small question just to finish. I guess these results can be done for exterior domains, and maybe it's more complicated for bounded domains, right?
Related to the wave equation, we can expect this kind of result, but for the wave equation, I'm not sure, because it's related. We work in light cone, then it will be hard to talk about.
It's more complicated. Okay.
But for the wave equation, we can expect this kind of result for sure.
Okay. Okay. Thank you so much.
Mohamed Ali?
Yes, Nili.
These results are available for any dimension or for some particular dimensions?
No, this is true for any dimension.
And you already said it, but then the domain is the whole space, I guess, no?
Exactly,
Here.
exactly.
Okay. And you say then that for wave equations, it's perhaps difficult to extend these results, but it's available for the heat equations.
The heat equation, exactly.
An exterior domain or bounded domain.
I believe, yes, I believe.
And do you know if numerical experimentations can add something to these, or nobody is interested with numerical
No, we have
experiments?
In fact, here the main important question is here PC. I try to move back to the equation. Okay. Here for the wave equation, I talked about the wave equation. Here P, I assume it, and even if for the pure case, that means once the nonlinearity is due to the P times U, here P is less than or equal PC. PC is called the conformal case, which is equal 1 plus 4 over n minus 1, which is of course less than PS. Then we have to understand the situation between PC and PS. I know there is some result, there's some numerical result, maybe Pizon and others proven, expected at least, then the behavior is similar until the Sobolev power. I mean the sub-critical. If P is less than PS, that means it should the result is true even between PC and PS. But just a numerical result, to be honest, I don't have a clear idea about this, but we expect this is true, and I'm not familiar about this point. But what I know is for sure between PC and PS, the behavior is similar somehow. We have the same result. For theoretical case, it's not easy. Why why we have this restriction? I can here once we move to equation in W, here we have the Laplacian becomes something like that, where we have some rho of y, which is 1 minus y squared to alpha of p. If alpha of p is positive, if and only if p is ps, then somehow we have a weight, we have a singular weight if we are between, if p is between pc and ps, then we have a singular weight. That's why it's impossible to talk about the energy in this case and to construct the Lyapunov energy, which is the main important point in this kind of result. But it's related to this limit. By the way, maybe we published a result, a weak result somehow in the supercritical case. It was 10 years ago, a weak result, which is a small improvement about result. Another result, we prove, we conclude some estimate, some smallness, but it's not the requested result. That means we have some rough result. We have control until exponential s. Not we don't we prove W is controlled by constant times exponential s and not bound, which is an improvement, but it's not the problem. The best estimate is not known until, even for the pure case, I mean.
Okay. Okay, thank you. Is there other questions, please? No questions? Okay. Thank you all for your presence, and thank you again, Hamdali, for this nice presentation. And okay, we hope see you next webinars.